Also, as Nicholas Copernicus introduced the heliocentric model, another astonishing amendment of how we may decipher the universe could emerge, beginning a conversation known as the development of cosmology. This rise is put aside by basic aberrations in our assessments and perception of the universe's essential properties, like its age, size, and speed of improvement. Neil deGrasse Tyson has noticed that the disclosure of the James Webb Space Telescope, JWST, has halted this conversation with a picture that opposes material science. So, what exactly is this crisis, and how does the James Webb Space Telescope add to it? Well, adding to it is somewhat of a deception. It's more like a review that has been in progress. The crisis alludes to how we could decipher the universe being tested, particularly concerning its age and size, which are associated by an extensive security buffer. The introduction of the JWST has been crucial in this context. Before this advancement, we were limited in how far we could see into the early universe. However, with the JWST's enhanced capabilities, space specialists can explore extensively more distant universes, giving us new perspectives on the universe and challenging some of our past notions. This progression permits us to peer further back in time, closer to the Big Bang, and observe systems as they were forming, providing essential data that can either support or challenge our current models of the universe. To grasp the crisis exhaustively, exploring its background is essential. The standard model of cosmology, known as the hot inflationary Big Bang model or lambda-cold dark matter lambda-CDM model, has been remarkably effective in explaining various aspects of the universe, from gravitational lensing to the structure of the cosmic web and the evolution of galaxies. The lambda-CDM model proposes that the universe began with a Big Bang, followed by a period of rapid expansion, and has been extending ever since. It incorporates elements like dark matter, which exerts gravitational forces, and dark energy, which drives the accelerated expansion of the universe. However, every significant observation, especially with instruments as advanced as the JWST, raises the possibility that our current model may be incomplete or needs revision. The lambda-CDM model makes explicit predictions about the properties and behaviors of galaxies at different stages of the universe's history. For instance, it predicts that galaxies in the distant past should be smaller, less evolved, and contain fewer heavy elements compared to those in the nearby universe. This is because heavier elements form in the cores of stars and are distributed through processes like supernova explosions, which take time to occur. The description you provide discusses how the standard model of cosmology predicts developments within groups and clusters of galaxies, as well as the properties of the cosmic microwave background, CMB. According to this model, galaxies should be smaller, bluer, less evolved, and poorer in heavy elements at great cosmic distances. This prediction implies that earlier periods of the universe would lack evident stars or galaxies. However, scientists have discovered problematic evidence that challenges these assumptions, resulting in a crisis in cosmology. The crisis in cosmology focuses on the uncertainty surrounding the universe's age. Different assessment methods yield varying results, forcing cosmologists to grapple with these discrepancies. To address this issue, researchers use several techniques to measure the universe's age. One method involves studying cosmic background radiation, unraveling the history of the universe's expansion, and employing mathematical models like the Friedmann equations based on Einstein's theory of general relativity to calculate the expansion rate and, consequently, the universe's age at different times. The CMB, a remnant radiation from the universe's early stages, is a critical tool for this estimation. Detailed maps of the CMB, such as those provided by the European Space Agency's Planck mission, offer valuable insights into the universe's composition. However, these maps lack data on dark energy, a crucial component of the current universe. Despite this limitation, researchers use the Friedmann equations and various observations to estimate the universe's expansion rate and determine its age. Another approach to determining the universe's age involves observing exploding stars, specifically type Ia supernovae. These supernovae serve as standard candles because they have a known intrinsic brightness. By comparing their known luminosity to their observed brightness, cosmologists can calculate their distance and, thus, the universe's expansion rate at different times. This method, widely used in the 1990s, played a pivotal role in discovering dark energy, which is now central to cosmological calculations. It is particularly useful for determining the Hubble constant, a measure of the universe's expansion rate. Although the Hubble constant is not truly constant, it is instrumental in mapping the universe's expansion since the Big Bang approximately 13.8 billion years ago. Observations have shown that the universe has been expanding consistently. NASA has noted the implications of this rate. If the expansion is slowing, it suggests an unknown force, possibly dark matter, influencing the process. Conversely, if the expansion rate is accelerating, it could indicate dark energy's presence and impact, driving the universe's accelerated growth. In January 2018, researchers discovered something intriguing. While some telescopes indicated varying expansion rates depending on the observation location, the Hubble Space Telescope measured faster expansion in the nearby universe, whereas the Planck telescope observed a slightly slower rate in more distant regions. This discrepancy highlights the vastness of the universe and reminds us of Edwin Hubble's groundbreaking work in 1929. Hubble's observations of distant galaxies revealed their recession from us, illustrating the universe's expansion. This discovery laid the foundation for modern cosmology. Now, considering the universe's expansion independent of your location, you would observe the same phenomenon at the same rate as the Hubble expansion rate. Early calculations were based on limited data, but technological advancements, such as the Hubble and Gaia telescopes, have allowed for observing more variables and refining our measurements. Different telescopes use readings of the CMB to calculate the constant. However, this method has its limitations due to the availability of supernovae for distant observations, restricting our view of the universe. Since discovering dark energy in the 20th century, researchers have been puzzled by the inconsistencies between these two approaches to the universe's age and expansion rate. As measurement technology becomes more precise, smaller variations emerge, driven by developing more advanced systems. This progress, however, raises more questions than it answers. Although the differences are minor, just 10 to 20 million years separating the estimates, the universe's approximate age of 13.77 billion years warrants careful scrutiny. One possible explanation for this discrepancy is flaws in our CMB measurements. Despite being among the most reliable estimations, the CMB has undergone extensive testing since its 2009 launch to validate its accuracy. Another perspective suggests a potential gap in our understanding of dark matter, raising the possibility that it may change over time and be linked to dark energy or another unknown factor. This idea has prompted various experimental studies. The accuracy of supernova measurements is also questioned, as the complexity of star explosions can introduce uncertainty into our models. Resolving this uncertainty in supernova models could help address the discrepancies in measurements. This crisis in cosmology has been further exacerbated by the James Webb Space Telescope's discoveries. According to Neil deGrasse Tyson, the JWST has found objects in the universe that challenge our current understanding. This suggests that our scientific framework requires a complete overhaul. However, the problem is that we have no idea where to begin to understand the magnitude of this scientific revolution. To explore the universe's origins, we must look approximately 50 million years after the Big Bang, when stars, black holes, and star clusters began to emerge, possibly as early as 50 to 100 million years later. However, these events should be relatively rare. What remains uncertain is how common galaxy formations were during later periods, spanning events between 400 million years after the Big Bang. Ongoing JWST images reveal galaxies much more distant and, therefore, older than the standard cosmological model predicts. This discrepancy suggests our model needs a significant revision. The discovery that the expanding universe relied on galaxies is a major breakthrough. JWST images show galaxies that formed much earlier than predicted by current cosmological models, triggering a crisis in the field. This issue is linked to galaxies and redshift, a common measurement in cosmology. According to the Standard Model, hydrogen appeared 400,000 years after the Big Bang when protons and electrons combined, leading to hydrogen recombination. This transformed the universe into a soup of hydrogen atoms, with some helium and residual background radiation. The gravity of this radiation acted on small fluctuations in the hydrogen gas, slowly pulling them together to form the first stars. These early stars, composed mostly of hydrogen and helium, participated in nuclear fusion, creating heavier elements like carbon and nitrogen. These elements played a crucial role in galaxy formation by absorbing heat and emitting cooling photons, facilitating the coalescence of gas into galaxies. The process of galaxy formation and evolution is complex, involving many stages. In the early universe, gas was primarily hydrogen. Over time, this gas became enriched with heavier elements produced in stars' cores. This process led to forming galaxies that contained not only hydrogen and helium but also carbon, oxygen, nitrogen, and other elements essential for life.